Okay, guys, let's start our second pedagogical set of lectures. Antonello from ICTP will make 3 lectures on Anderson and many-body localization,
Yes.
right? Yeah.
Yes, well,
Please.
thank you, Dario. Thank you for the invitation to all the organizers. It's my first time in Brazil, I have to say, and so far I'm having.
You already joined the PCAD.
Yes, yes, yeah. 2 different places actually. So I'm collecting statistics. Okay, good. So this will be pedagogical lectures. So I apologize in advance to colleagues and also students who might be well versed in these things. And if you want to leave, please do anytime. Okay, so the idea of these lectures is to give you some more details on things that people have already discussed. So we had several talks in which we had in disguise a small disorder expansion. We had a locator expansion for different models and different things. And what I want to do is to go a little bit deeper into these topics, which were born essentially with 1958 Anderson's paper. The small disorder, actually it's much earlier. And they exist, and they are techniques that I think everybody working in disordered systems should know. Okay, good. So, yeah, so the syllabus will be this. So today I will start with the small disorder and show how we go from ballistic to diffusive in the quantum setting. Okay, so classical quantum. And then we'll see what indications does quantum mechanics give us to warn us that, in fact, there might be, and this was Anderson's great intuition, one of Anderson's great intuitions, there might be a breakdown of diffusion. Okay, so if there is a breakdown of diffusion, there is no conductivity, the system becomes an insulator, and an Anderson insulator in this case. And then we enter a large disorder phase. So in the large disorder phase, we need to show that the large disorder phase is indeed stable. Okay? So we need to do a completely different expansion around the large disorder. This is called the locator expansion. And then argue that this expansion converges for disorder sufficiently large. Okay, so we have an expansion which converges hopefully for small disorder, one which converges hopefully for large disorder. There must be a transition in between. Okay? And the third lecture will be investigating what we know, and also I will give you more details about the recent works that we did on describing the transitions all the way to infinite dimension. Okay, so, and then that should be it. But if time allows, I will actually discuss, I would like to discuss in this view, in particular in the perturbation theory setting, which is the original setting of Vasco and Schuller, what MBL is in this thing, okay? All right, good. So first of all, classical diffusion. Why is it important? Why is diffusion important? First of all, because we see it, it's very generic, okay? We see it essentially anywhere. Okay? So if we have a particle, so and also it's connected with the equilibration, and it's connected with a particular form of equilibration. Okay, so for example, if I give you, which is the Gibbs distribution. So let me give you, for example, let me give you a random walk in which in a time dt, the momentum changes by this, and then there is some absorption, okay, and some random force, right? And in the same time dt, the position of the particle as changed by this. Right? And what I want is that this force is random and has correlation 0, at different times, okay? D prime, and then there is some diffusion coefficient in momentum space, dp. Okay. And okay, there are vectors, vector indices we can put here. Okay, good. So I assume you know how to go from random walks to Fokker-Planck equation, which describe the evolution of the probability distribution. And the evolution of the probability distribution gives you a nice equation, Pi minus dV over dQi minus gamma Pi times rho, summed over I, minus d by dQi, Pi over m times rho, plus dP, sum over I, d squared, dPi squared times rho. Okay, and rho is the probability distribution of finding the particle at phase space position QP at time t. Okay. Now, if I want the equilibrium distribution, I need to equate this to 0. Okay? And then it's an exercise for you to show that this thing actually satisfies this equation. Okay? If I set beta, which is equal to gamma m divided by dp, okay. Good. This is not the diffusion coefficient yet, okay? So it's the diffusion coefficient in the momentum space. But then what I can do is to scale dp, gamma, and m, okay, in such a way that I can send dp and gamma to infinity and keep this ratio fixed and keep this ratio this is a fixed, okay? This is a way of getting the overdamped limit. So if you do this, then this entire equation here becomes d rho by dt is equal minus d by dqi mu f I, which is a force, times rho, plus d squared dqi squared times rho. Okay? So we have eliminated momentum doing the overdamped limit, and we ended up with this. Okay. So diffusion and the Gibbs distribution are linked. Okay? It's very difficult to have a dynamical system which has diffusion and doesn't go to equilibrium distribution, which is like this. You can build counterexamples, but they are artificial. So typically, diffusion and Gibbs distribution, they go hand in hand. Okay? This is for the classical. Okay, now quantum mechanics. How do we find diffusion in quantum mechanics? Okay, the first thing we want to do is correcting, but for the moment it's just phenomenology. Okay. Oh, mu is the mobility, and it is given as one over m times gamma. Okay, so I've taken this, the limit gamma in dp that goes to infinity, and I traded it for 3 different things. Yeah. All right, good. So Fermi-Golden rule. So technically, what is the Fermi-Golden rule? Fermi-Golden rule is the following thing. I have a continuum of states. Okay. I prepare my particle in a state here, and I compute the rate of decay of this state in the continuum. Anything goes, okay? For example, you have the hydrogen atom in an excited state, okay? The hydrogen atom in an excited state is perfectly stable. You couple it to the photons, which are a continuum, okay? The hydrogen atom can decay, okay? And you can compute the rate quite easily. Let's specialize to this case. By the way, apparently Fermi was not aware that this was called Fermi-Golden rule. Yeah.
Until the end, he didn't know that people.
Well, I mean, no, somebody told him, I'm using your golden rule. And he said, which one? No, he thought that it was his golden rule. In his mind, golden rule was something else. I mean, no. No. Oh, maybe. I mean, he was not known to be a modest person. Anyway, okay. So let's start with the plane wave. Okay, a plane wave in the p direction in a box of volume B. Okay, so in space representation, this is e to the px divided by h bar. Okay, good. All right, and let's take our Hamiltonian to be the Hamiltonian for which this is an eigenstate. Think the hydrogen atom decoupled from the photons, and therefore this is p squared divided by 2m. Okay, and then let's add the perturbation. Perturbation is a potential, and again, I want this potential to be essentially uncorrelated random noise. Of course, if I show something like this, which is a differential equation with the random noise here to a mathematician, they just say, okay, that doesn't exist. Okay, so so to make our mathematicians friends happy, what we do is, let's say this as a decay, which is over a length scale L, which is pretty small. Okay, so it's correlated random noise, but with small L. Okay, very good. For all practical purposes, this is like saying I have L to the D, delta function of x minus x prime times W0 square. Okay, in this way, this is dimensionally correct because this is dimensionless. This is a dimension of energy squared and energy squared, and then this is dimensionless. Very good. Now, Fermi-Golden rule tells us that the decay rate gamma for P to anything else, okay, is pi times the integral d dp prime over 2 pi h bar, yes, h bar to the d of delta function, the energy of the initial state minus the energy of the final state, okay? And then matrix element of our initial state squared. of the perturbation of the operator square. Okay, so since that's square, okay, and this is an integral in the x of px w of x x psi, okay, and then we square it. We have two integrals over positions. And then we have e to the p minus p prime x minus x prime. And then we have wx prime. Okay? Good. Now, if our momenta are, our wavelength differences are larger than the length L, which I'm assuming is the smallest length in the system, I can substitute this with its average. Okay? This. Actually, I was using brackets like this. And so I get a nice delta function. And I get W0 square times L to the D, integral ddp, 2 pi h bar to the D, delta Vp minus Cp prime. 1 over V, sorry, there was 1 over V from here. 1 over V, W0 squared. Okay, that's all. Okay, good. Now, and I'm left with one integral because one integral goes over dx. Okay, so the rate goes like, now, okay. So now we encounter something, a concept which is very, very important for all the rest of discussion on Anderson localization, the local density of state. Okay, so let me break this as, now this and this go away, okay? So this is the local density of state, at which point we have averaged over space, right? So at every point, at any point, actually. Okay, so this is pi W0 squared times L to the D times density of state of, let me put the reference point x0 at energy EP. Okay. The local density of state is independent of the point x0 on which I go and measure it. This is important because it's exactly this independence that will break down when we have localization. So it doesn't matter where I put my particle, okay, in my disordered system. It doesn't matter where I put my particle in my disordered system. The local density of state, if disorder is sufficiently small, will always be the same. Unless there are big modulations on top of the disorder, we are not considering those, okay? So if I do an experiment and I measure the local density of state, that depends on the position where I measure, it means that, and I'm sure that my sample is statistically uniform, then there is a localization phenomenon, okay? This is important. Okay, very good. So what happens then? It happens, you see, I was very careful to keep the units consistent, right? So this is an energy because it's h bar times a rate. This is energy squared. This is 1 over energy times volume. This is volume, so we get the units are consistent. Very good. Okay. So now Now, if I initialize my state in a packet, wave packet, okay, of momentum around the momentum P, which has a certain group velocity, Vg, then this wave packet will move and will scatter. Okay? There is a probability of scattering per unit time, which is that gamma, to essentially any other, it will be S-wave scattering, okay? So there is no, W is a scalar, okay? So it's S-wave scattering. It's scattered with the uniform probability over the sphere. So this was coming with a certain momentum P, and then the momentum P prime, because of the energy conservation, must have the same norm, okay? So the only thing it can do is change angle, okay? And it does this every time tau, which is 1 over gamma, okay? And which is therefore proportional to 1 over W squared. So this keeps doing this. Okay, so there is, this is actually the collision time is a Poissonian distributed variable with a certain mean, okay? But let's assume it's always the same. So, so it does this random walk, okay? And the diffusion coefficient will be the group velocity squared times tau. Now, the group velocity depends just on my initial energy and the dispersion relation, but this is p squared over 2m, so it doesn't matter. And this thing here depends on the disorder. Okay. So the diffusion coefficient is 1 over proportional 1 over disorder squared. So if I plot this thing, diverges when W goes to 0. And this is the region that Anatoly has been talking about this morning. Okay. And then this goes down forever and ever and ever. Now, I can compute further corrections to this thing. Okay. They will give me higher power of W. So actually, this might change from just 1 over W0 squared, but it's never 0. However, this is all semi-classics. Okay? So what is when can we apply semi-classics? Well, when the wavelength of my particle is much smaller than the distances over which something happens.
Because here I'm still treating, let's say, a free particle, and this Wx is the disorders.
Yes.
When do I see that this is semi-classical? Because I'm thinking in terms of collisions.
Yeah. So first of all, this is a perturbative expansion in W, right? Okay. In fact, the condition that I'm going to tell you, the condition now is that the wavelength lambda, okay, the de Broglie wavelength lambda, must be much smaller than the mean free path. Okay? The mean free path is the group velocity times the time tau. Okay? Now, the group velocity is p over m. Okay? The time tau is 1 over W squared, but there is the density of state as well. Okay? So let's say it's 1 over W squared. The density of state also depends on the momentum. And this thing here is h bar over p. Okay. So you see that if I go to very large W0, okay, then this inequality is not going to be satisfied anymore. And physically, what's going to happen? What do we expect the diffusion coefficient to do? Well, I mean, I'm scattering my wave. Okay, so my wave has a certain wavelength. This is the first 0, then there is the second 0, and so on and so forth. And I was scattering here. before my wave has changed its sign. Okay? So if it scatters before it changes sign, the interference path coming back from here at the same wavelength is going to make positive interference. Okay? So when lambda becomes of order or smaller, or larger than the mean free path, I have positive interference with myself. Okay? So the particle tends to move less, and the diffusion coefficient starts to deviate from this nice semi-classical calculation. Okay? Now, the intuition of Anderson was that indeed this deviation is catastrophic, and at a certain point, the diffusion coefficient actually goes to 0. Here there is the divergence, okay? The diffusion coefficient divergence when W0 goes to 0 for obvious reasons. Okay, if you take this thing here, put the density of state, and compare, you find that this is also the condition for the kinetic energy to be larger than the fluctuations of the disorder, okay? Anyway, okay, good. So what happens when this thing happens? Then the details of the disorder start to matter a lot. And this density of state stops being self-averaging. Okay. The diffusion coefficient defined in this region here, so this is the region lambda much smaller than mean free path. This is the region lambda much larger than mean free path. Okay. Good. What was I saying? So in this region here, that thing starts fluctuating, okay? And in this region here is completely point dependent. Okay. The fluctuations here at the transition here, okay, they are very peculiar, and they are all these multifractal states that you have heard about. Okay, good. So I think I like the Lev's plan of stopping at 45, 50 minutes and then doing a 10 minutes break. Would that work?
Yeah.
Okay. Very good. All right.
What was the reason that the diffusion state now is after this point is now dependent on the state? What's the reason?
Okay, so first of all, we are not granted that this is going to happen. We have to prove it. Okay. With insight, with actually 70 years of insight, I can tell you the answer, what it is. So when the disorder is very strong, the local properties, they matter a lot. So you put your particle on a site, okay, and then you look at the neighbors, okay? And essentially the density of state will tell you how much in resonance off resonances these neighbors are, and this is not washed out by the existence of plane waves. There are no plane waves, okay. So everything is very local, and if it is very local, it's attached to that particular disorder realization. So that rho will follow the local disorder realization.
So in this point, it goes from like from plane waves to very local? No?
Yes, exactly.
Oh.
So here, before the transition, the eigenstates will be plane waves, modulated, changed a little bit. Okay, the dispersion relation will change a little bit because the disorder is not that it doesn't do anything, but they are plane waves. Okay. After the transition, they are localized states.
Perhaps can we rephrase that? Let's say the problem of this approach is that among the assumption, there is the assumption of a continuous spectrum that at a certain moment is not valid. So you don't see the problem because somehow you're working in an assumption that is simply not valid anymore.
Yes. So the spectrum is, okay. So the spectrum is always continuous. Okay. The spectrum doesn't change. It's the matrix element that change. Okay. So the matrix element between wave functions now become, the spectrum is always this. So there are always, and if you have, you know, your band and you have a volume V, you have, okay, let's go to the lattice. Okay, we have a lattice with V points, N points, okay? And the band, single particle band, is of order of the hopping, T times number of dimensions, more or less, okay? Times the number, 4, it depends on the lattice, right? And you have n states in this band. Okay, when I take n to infinity, this is becoming a continuum. What changes is that this state here, it's going to be concentrated around this point here, and the neighboring states are going to be concentrated around points which are really, really far away. So this matrix element, it's 0 most of the time. Okay, so mathematicians say that this goes from absolutely continuous to pure point spectrum. That's the terminology in math. Okay, so if you look at the density of state, at a given point x, as a function of the energy E, it goes from being a smooth function for any x, okay? Actually, what I plotted is what usually people plot, which is the cumulative distribution function, okay? Because this smooths delta functions into steps. So the CDF is smooth, and it's the same irrespective of x. What happens is that this thing will become a staircase. And this staircase will depend on the point x. Mathematicians call this pure point spectrum and this absolutely continuous spectrum, because this measure can be split using Lebesgue theorem into an absolutely continuous part, a pure point part, and there is also a singular continuous part, but we never figure out where that fits actually. Maybe the critical point. Okay. All right. Now let's do a proper propagator calculation. Okay. Let's go on the lattice. Now, why do I want to go through the pain? So we understood this thing. This calculation is correct. The physical interpretation is correct. Why do I want to go through the pain of doing everything using propagators? Because it's very useful as a technique, even in, for example, many-body cases. Okay, so for example, some of the things that Tobias has shown us with, you know, those wiggly lines between advanced and retarded propagators, they come exactly from this thing here. And in my mind, they are easily understood, more easily understood when you talk about single particle. But then the same technique, since we are talking about matrices, the same technique goes through for many-body or random matrices or whatever you want. Okay. All right. Okay, now let's write our model. We have a lattice. For the moment, think of just a lattice, just, you know, a graph with vertices. Okay. It can be anything. This is the bracket notation, okay? Because you have, I mean, this. So it says there is a rate t for my particle to hop from J to its nearest neighbor I, okay? And when the particle is on the site I, it has an energy epsilon I, okay? The energy is epsilon I, so our mathematician friends are happy, are random variables distributed between minus W half and W half. This is called the Anderson model. There are other models of disorder in which, for example, you don't have this term here. You have disorder on the couplings. They're very interesting. The phenomenology is slightly different from these things, but they also have localization transition. Sometimes in literature, you find them referred as Lifshitz models. Some people call them Dyson models, some people Lifshitz models. Okay, very good. So, let's look at propagators. Okay, so of course, as usual, the Schrödinger equation is this thing. Okay, let's look at propagators. Propagators are the inverse of they're the resolvent. Okay, but since we expect the system to have continuous spectrum, we need to shift away from the spectrum of the Hamiltonian. Otherwise, this matrix is not invertible. Okay, so this means that we have to define two retarded and advanced propagators in which I add a small imaginary part or subtract a small imaginary part in such a way that I move up the spectrum or below the spectrum. Okay. Okay, very good. Of course, these are matrices and they have matrix elements. The matrix, the density, local density of state, rho of x, okay, E will be sum over all the eigenstates, psi a x square delta of E minus EA. If there is a continuum, this is an integral over dEA. Good. Now, as usual, by looking at these things here, I can write this thing as the imaginary part of GR, or I divided by 2 pi, the difference of the matrix elements of this operator. Okay, good. And now let me build a wave packet. Now let me build a wave packet which is concentrated around the point of x0, okay? But also has is also concentrated in energy. Okay. So can I do it? Sure. There will be a trade-off. Okay, I want to make a semi-classical limit. Okay. And this A is a normalization. Okay. Now, from this, so actually let me call this psi 0. From the normalization of psi 0, okay, I leave it to you as an exercise to prove that this is equal to 2 pi sigma A squared times density of state at the point x0 and at energy E0, okay? From which I deduce that A is 1 over square root of 2 pi sigma rho of x0 is 0. Okay, good. Now, let's look at the probability distribution, the probability, actually, to start from a point x0 at time 0, okay, and end at a point x at time t. I'm just saying, take this particle, take this psi 0, evolve it with e to the minus ht, okay, and then project it to x. And then take the square. This will be a divided by 2 pi integral in energy dE retarded propagator x0 energy E, and then we have our wave packet filter e to the minus E0 minus E square divided by 4 sigma square modulo square. So you might notice that these two things, independing of whether the spectrum is continuous or not, these are complex conjugate, okay? So here I have two integrals over the energies. That I rewrite as integral of an energy, which is the average, okay, and omega, which is the difference. You should be, I mean, the same thing we did when we discussed, when Lev discussed the ETH. Okay, and then we have G retarded x0 E plus omega alpha, G advanced x0 E minus omega alpha, and then we have a bunch of things. We have e to the minus I omega t, which is the difference, okay? And then we have things like e minus omega alpha minus E0 squared divided by 4 sigma squared, e minus e plus omega alpha minus E0 squared divided by 4 sigma squared. Okay? Good. Now, assuming that omega, so we assume the following thing. We are looking at time t, which is much larger than h bar over sigma. Okay, so we don't have, and also much larger than h bar over E0. So when we do this thing here just becomes, we can neglect omega with respect to E and E0 here, okay? So this becomes Gaussian integral in dE, which essentially fixes the energy E at E0, compensates for one of the factor A, and the final result is 1 over density of state at point x0 at energy 0 times integral in the omega, that now we can extend from minus infinity to plus infinity, e to the minus I omega t, g retarded x0 energy 0, g advanced x0 energy E0 minus omega. Okay? Okay. So this is in the semi-classical analysis is an exact expression. Okay? I haven't done any average anything yet. If I know what G is, I can put it in here and then do the calculation. Okay. Of course, I don't know what G is because this is a random thing. Okay. And yeah, so, and that's it. Okay. So notice that at this point, even though I've done some approximations, I've never lost the normalization. Okay. If I take the sum of x of p of xt x0, 0, I get 1. Okay, just do it if you want. And now I have to average over disorder. So when I average over disorder, I have to average this products of retarded and advanced propagator. Okay. So I go from the point x0 to the point x, and my retarded propagator, I put an arrow like this. Okay. And again, I have another propagator, x0, and I go to x, and I put the arrow in the opposite direction. Okay. This propagates at energy 0, this propagates at energy 0 minus omega. Okay. Good. Okay, now we can do perturbation theory small disorder. Okay, let me just write down the expression. Okay, so my point was not to torture you with all this algebra, okay? My point was to show you that when you look at interesting quantities, the product of GR and GA arises. Look at the density of the local density of state here. There is GR and GA separate. If I take the average, I take the average of this minus the average of this. The average of the density of state is equal to the density of state and does not know anything about Anderson localization. What knows about the Anderson localization is the fluctuations. So what do I have to do if I want to see the fluctuations? I have to square this thing, right? And if I square, I get products, GR and GA. The products, retarded and advanced, are the ones that know about the localization. Whether you look at it as a function by the fluctuations of the local density of state or by the physical measurable probability of finding the particles at position x at time t, it's the same. You will always end up with products of GR and GA.
Assumption that you did from the second line to the third.
Oh yeah, here that E is very close to E0. Okay, so sigma is small, and omega is smaller than E and E0. Okay. That we are not looking at ultra small times or ultra large frequencies. We are looking at long times. Okay, that in such a way that our packet stays more or less makes sense. I mean. Okay, good. Okay. Yeah. Yes. Okay, let me tell you what I'm going to do after the break. After the break, I'm going to use the fact that, you know, H is equal to H0 plus disorder, okay, W, okay? And this gives me that G is G0 plus G0 W G0, both retarded advanced, plus G0 W G0 W G0 plus blah, blah, blah. So the usual perturbation theory in W. And I'm gonna try to take products and averages of these things. Okay? Let's make a 10 minutes break. we are looking at small disorder, let me do perturbation theory in disorder, okay? So I'm using the series which comes from the identity. This is an identity, okay? This is an identity, valid both for retarded and advanced, doesn't matter, okay? So if I iterate this equation, I get a series. This plus 2 scatterings, multiple scattering, okay? Okay, what does it mean? Okay, so if this is my retarded propagator from x0 to x carrying energy E, okay? Diagrammatically, I've written this is like the free propagator without disorder, plus from x0 to x, plus diagrams in which I scatter over position x prime on my way to x, okay? And then I get an amplitude W of x prime. And then I have to sum over all the x prime, right? And then I scatter again, x prime, x second. And then I go to x. And then I scatter 3 times. And so on and so forth. Good. Now, plus blah, blah, blah. Okay. Now, this is G0 of x, x0 energy E. G0, sorry, I need to sum over x. X prime E, W of x prime, G0 of x prime, x0 E, plus sum over x prime, x second, W, x prime, W, x second, G0, x to x second, G0, x second to x prime, times G0, x prime to x0, plus blah, blah, blah. Okay? Good. Now, this is the retarded propagator. The advanced propagator is the same. Okay? It has completely analogous series in which I just invert the arrows. Now, the thing I should do is multiply these two series. One is computed energy 0, the other is computed energy 0 minus omega, average over disorder, and see what I get. Before doing this, let me do first an approximation. Let's see what happens, okay? Let's do the approximation in which the product is substituted by the product, the average of the product by the product of averages. Okay, this is called Drude-Boltzmann approximation. Okay, if I do this, this means they just need to look at one of them. Now, when I average over W, what do I get? This term is unscated, right? It's just the average to itself. It does not depend on W. This term is 0. Okay. What about this term? Well, this term, the only non-zero term in this double sum is the term in which x and x prime are the same. Okay? So since the average of W x prime x, now I'm on a lattice, okay? So I'm just is equal to Kronecker delta, and then there is some W0 square. Okay? This depends on the distribution of disorder, so it doesn't matter. Okay. So when I average this thing, this goes away. what happens to this? This becomes this. X prime and X second are the same, right? And I have a loop diagram. At this level, the disorder is like an infinitely heavy particle. Okay? In which, like, think of a Yukawa interaction, which you have a range of interaction. And then this particle is emitted and then reabsorbed. In order to be emitted and reabsorbed, if it has infinite mass, the two things have to happen in the same position. Okay? Now here, well, this is going to be 0. Okay? The other ones, and then I have the four interactions, okay, which I have neglected. Okay, now these things have to couple to each other. Okay, so when they couple, this thing can shrink in two ways. It can either become this, or it can become this contracted with this and this with this. So this would be something like this and this. Okay. And so on. So any order, at 6 order, I will have this diagram plus a bunch of other things. We don't know how to resum the entire series, okay? So usually when you have this kind of things,
And these are not, there is no suppression between they are both in rooms, so they have the same order.
in principle, yes. In W, yes. In practice, this actually is slightly smaller.
It's suppressed.
It's suppressed in the region where we are looking at, okay? But for me to prove to you this at the moment will be a mess, okay? All right, good. So do you know what we do? So suppose we want to take now this diagram plus this diagram plus this diagram plus this diagram plus so on. Can we resum this series? Yes. Okay. We just define this thing as the self-energy. Okay. And then my diagram, my series is G0 plus G0. I think it's a sigma G. Okay. In this approximation, it's an approximation. It's an approximation. So this the solution of this thing is formally 1 over G0 minus sigma. But now, what is this diagram? This diagram is what comes from here, right? So if I put x prime and x second equal, this is G0 of x prime at energy E, which is, since G0 is the particle, the free particle, it doesn't matter what point I measure, it's always the same, right? So it's G0 of the origin, for example. Okay. Good. Very good. So maybe we have made some progress. So in this approximation, in which I select these diagrams and I resum them, I just have to add, my average G, retarded / advanced, is 1 divided by E minus H0, which is P squared divided by 2M, or whatever it's on the lattice, okay? Whatever the kinetic term is on the lattice. And then I have the self-energy, okay? Now, the self-energy is G0 of 0, 0, E, and if you remember, I've erased it, but essentially It's what you use to compute the density of state. Okay? There is a W square, which multiplies this thing. So we have W square times W0 squared times G0 of 0, 0, E, which has a real part in principle and an imaginary part. Okay? The real part is reabsorbed in the definition of the energy. The imaginary part has a more disruptive effect. Okay? So let me write it as 1 over h bar over tau. If you do the calculation properly, density of state and everything, this is exactly what comes out from Fermi-Golden rule calculation before. Okay? So this is really the decay rate of the particle with momentum, with a given energy E and therefore momentum. Okay, good. Now let's look at our Drude-Boltzmann approximation.
So the approximation you're considering here is a specific form for these correlations, or was there any other approximations that you used?
The approximation is I have an infinite series of diagrams. I more or less arbitrarily select an infinite subsequence of diagrams and resum them.
I see. And do these loops appear because you are factorizing higher order correlations into this form?
No, because no. This I need to explain better. Okay, so let me take the average of this term here.
Yes.
Okay, then what happens to this term here when I take the average?
You get the deltas. And then
I get a delta x prime x. Now I have to sum over x prime x second, sorry, x prime x second with the delta. So let me sum over x second. And so what do I have? Then x second becomes x prime, this becomes x prime, this is x prime, this is x. So this is a constant independent of x prime. I take it out and I have to sum. So I have W0 squared, G0 of x prime, let me put 0, 0, 0, E. And then I have to sum over x prime, G0, x prime, the remaining two terms, this one and this one. Sorry. Now, this is a matrix product. Okay? So I can write this thing as, this is a constant. Okay? I can write this thing in the form constant times G0 times G0. Okay? And then I write the other terms. And what all the other terms do, this subset of diagrams, is essentially they modify this G0 into G. And now I have a Dyson equation. Dyson equation for a matrix, okay? Where this is a constant. This constant has a real part and imaginary part. Forget about the real part. Let's look at the imaginary part, okay? And when I resum the Dyson equation, I get this thing. Good.
But approximating the self-energy with the Baire propagator.
Yes. I'm considering just one loop. So the other things will be two loop, self-energies, and so on and so forth.
Yes, that's what I mean. If you consider these two loops, they arise because then you have like a product of 4 W's, and then you want to take the average, you have to factorize them, and then you get this.
Yes. Yes. We don't appear at second order, there is only one. At third order, we have 0 by parity. At fourth order, assuming Wick, the Gaussian distribution for this thing here, then I have two different things. One is essentially belongs to the same family as this. The other one is new. Okay, so in principle, I should resum all the other diagrams, which, for example, are relatives of this one. So this one, for example, or this one, and so on and so forth. And then this will give me a series of, for the self-energy, this gives me what they are called sausage diagrams. This, okay, they are higher order in W, 0 squared.
More in the lattice, no? So should I think this X as the lattice size, or should I think about this X?
No, 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 I'm summing over X. This is discrete variables, and this is Kronecker deltas.
No, the system, the model was a lattice.
It is a lattice. It still is a lattice.
I think about this X as a lattice points.
Yes.
Okay, so it's calculating with the lattice. But now the disorder in the model was the energy. This disorder also is in energy.
Yes, it's the important thing is that it's local in X.
Oh, okay, so it doesn't change.
It's local, right? It's the important thing is the locality of the disorder and the fact that it's uncorrelated from side to side. Okay, good. All right, so we have this thing here, and let me take the X. So I want to do this, right? I want to do this times this in the X representation. Now, this I leave it to you as an exercise to prove that given this form as a matrix, the matrix element x0 at energy E is equal to minus pi rho local density of state of E0, E retarded advanced. The only thing that changes is that you have a plus and minus I K times R minus R divided by 2L. Now I'm going to explain what K, R, and L are. K times R, okay? Where R is the distance between the points. K is the momentum divided by h bar, which is 1 over h bar, square root of 2m is 0, okay? L is P over m times tau, okay? Now, this is exactly identical to the propagator of the Schrödinger equation, free Schrödinger equation, with an imaginary part, okay? The thing you have to do is to do it as a function of E, okay? And then put E plus or minus I h bar t in the retarded advance, and then you're going to find this. Now, okay. Now I have to multiply these two terms, one computed at energy 0, the other energy 0 minus omega. Divide by whatever was. There was a 2 pi here. Yeah, because there's a 2 pi squared here. There's 2 pi here. Okay, good. So this becomes pi divided by 2. Density of state, local density of state at energy 0. And then I have e to the I square root of 2m E0, okay? Minus I square root of 2m E0 minus omega times R minus R divided by L divided by K square R square. You put the local density of state in 3 dimensions, and this becomes expand for small omega 2 leading order in omega, and this becomes I omega R divided by V minus R over L divided by 4 pi R square. Okay? This is this part here. of this thing, I have to do the integral in the omega. And I have to add e to the minus I omega t. Okay, so this is the Drude-Boltzmann approximation. Very good.
The level of doing the Gaussian average, the factorization, plus the first order.
Yes, yes. Okay, so you see that this thing in the omega is the delta function. And so in the Drude-Boltzmann approximation, the probability to find x at time t being at 0 times 0 is delta function of r minus bt divided by 4 pi r squared e to the minus t divided by tau. There is a problem. First of all, this has nothing to do with diffusion. It looks like, you know, ballistic motion. You know, at time t, I'm at r equal vt, then divided by 4 pi r squared. This is the first problem. Okay, we haven't found diffusion. What's the second problem? What does this thing do? If I integrate this in dx, this will give me 1. But this will give me e to the minus t over tau. So having split the average over the product of averages, even broke normalization. Okay, so it's a really bad approximation. We are losing, particles are disappearing in our approximation. Okay, so every time it scatters, it just goes away. So we need to do better than this.
But why is it because of that it could be also because of that it's too early there?
It could be, it doesn't. Okay, because what happens if you add more orders, you just change tau, but the form stays the same. It's the correlations between the retarded and advanced, which are okay. All right, now we need to step up our game. Now we really need to take the product of the two propagators. Okay, is this clear? So we have, you know, approximated. By the way, I find it really fantastic that we got all the, if you really do the calculation, I'll give you, I have written notes. This is a part of a class that I was teaching at CISA up to a couple of years ago. It's really, if you actually do the calculation, you find all the 4 pi r squared. It's really, you know, it goes through, despite all the, oh, this is approximately 1, oh, this is this is that. It actually works. Okay, so I find it really surprising. Anyway. Okay, very good. Okay, this we keep for a second. Before I forget, this part I've taken from Ackermans and Montambeau, which is a very nice paper, a very nice book, sorry. It's related to a certain, it's actually dedicated to a certain, let's say, community of mesoscopic physics. So it goes into the details on a lot of things for people who are more interested in more general discussions. It's you can skip entire chapters, but they're actually, it's actually a very good book because all the calculations are actually done in detail. Okay, and I like that because, you know, if you can do a calculation, you should do it. All right. Now, let's take our two retarded and advanced. Okay, so we have this plus this plus this, okay, plus blah blah blah, multiplied by this plus this plus this plus this plus. Okay. Now, when I take the average, I can contract this. This I cannot contract with anything. Sorry. So I can. Sorry. No. Now I can contract this with this. Okay. This can contract by itself, or I can contract it with other things in here. So I have many, many more diagrams. Okay. If you remember, in one of the talks, I think Monday or Tuesday, I don't remember, there were these wiggly lines that meant that you were contracting disorder, and that was for matrices, but it's exactly the same thing. So good. So what can I do? Let me reorganize the series in such a way that I take lines that when there are contractions inside the same line, I just put a double line for the average GR. Okay. So this means that I've already resummed all these diagrams. Okay.
And, sorry, including also, for example, again, the diagram like this is included. So this is the full propagator with everything.
Yes. Now this, and then I do this thing here. Okay, so if you take the bare propagatory of bare, contract these two, is like contracting this diagram. And then there is the entire world. Okay. So even if I assume that I'm able to resum all the diagrams inside the retarded or advanced propagator that do not contract with the other things, then I have everything else. I have things like this, right? I have this that contracts with this. But I also have other things. I have these things. Okay, plus blah, blah, blah. The approximation in which I select this, plus this, plus this, plus the ladder diagrams, it's called the diffusion approximation or diffusion diagrams. Okay, so I went one step beyond. I'm considering not all the possible diagrams, but only a subset of diagrams, okay, in which I have this thing and then a ladder, then these things, and so on and so forth. So they occur in the same order. Good. Can I resum this thing? Yes, because I now have an equation for P. My equation for P in the Fourier, so the Fourier transform. P diffusion x0 omega is going to be P0. Now I have a Dyson equation for P, okay? For P of x0 omega, which is proportional to GRGA. The proportionality constant is the density of state. So I have P0 of x0 omega plus this thing here, which is going to be h bar over, actually, yes, I think it's h bar over tau, sum over x prime, p0, x, x prime, omega, p of x prime, x0, omega. Okay, so this is the Dyson equation, PD, sorry. Dyson equation for the diffusion. I've resummed all the ladders. As I was resumming all the self-energies for the propagator, this is exactly the same thing, only and this is a matrix, okay? Again, if this is a matrix, then I can solve this by going to Fourier transform, okay? And Fourier transform, this becomes P, in X, I mean. I go to momentum space. Q omega is equal to P0 Q omega plus H bar over tau P0 Q omega PD Q omega. So solving this equation here, we find PD Q omega is equal to 1 over P0 minus 1 Q omega minus 1 over tau. So the only thing that I need to do is to find the Fourier transform of this object here, both in space and time, invert it, add it here, subtract minus 1 over tau, and then hope that this actually is now a diffusion.
By taking the self-energy only at the first order, so this P0 is not including, I mean, it's including the summation of the
yes,
geometric series
yes,
at that level, and that,
yes,
so okay, so
yes,
you're doing two approximations.
yes.
Okay.
Yeah, we're doing many approximation.
Okay.
Yes.
Okay, just to...
Yes, two approximation. Yes. Okay, so my guess is that if I add more sausage diagrams and other stuff to the self-energy, the only thing I'm going to get is that this tau is going to change. Okay.
If I read that what you effectively done is that the draw you have has just come from the average of a single diagram. If you make it many more, if you go all that, the average of those, and it will have the same draw.
Yes.
Okay.
Yes.
Okay. Sorry, just to remember, the fact that you have two omegas there, sorry, two W there is because you have 1 over tau. You are substituting the, I mean, in the second term, exactly, this 1 over tau is coming from.
Yeah, from this. You have two of them, yes. So you have whatever happens at stays within the retarded propagator, and that is going to be P0. And then there is this W of X prime, the contract, and okay. Right? So we need to do Fourier transform of this thing. Okay. And the Fourier transform of this thing is a max. It shouldn't be, but it is. Let me tell you what it is first, and then why it shouldn't be. This you don't find on Ackermann's and Montembeau. I had to do the calculation myself. Okay, this is a mess, but if I look at small q and small omega, this is nothing but minus I omega plus dq square plus 1 over tau. Okay, now, why this shouldn't be a mess? Because if you think, I could have done this already. Sorry, whenever I have GG, okay. So what this one was it was the product of two G's in real space, okay. And then I have to do Fourier transform, so I have to do I can do the convolution of of the two propagators with different momenta. Okay. If you do that, first of all, it diverges because it has, depends on the integral. You have two, diverges if the dimension is sufficiently high. Second, you get a mess of a function of omega. And it's not clear you can actually get this function so easily. In fact, in order to obtain this equation here, what did we do? We went to small omega term before. You remember, we had the square root of energy minus omega. We expanded to first order. So already in getting this form here, there is already a small omega expansion. Am I using it already here? Then I redo a small omega expansion, small q expansion, and I get this. This 1 over tau here is exactly this decay time here. And now, no surprise, when you do this just cancel that. And so this is 1 divided by minus I omega plus dq squared, where d is 1/3 v squared times tau. We even get the 1/3 correct. Okay? So if I do this approximation, I get the diffusion pole. Now, if I do the Fourier transform of this, everybody knows what it is, right? It's xt is e to the minus x squared divided by 2 dt divided by square root of 2 pi dt. Actually, to the d. And we know that this is normalized. So adding these diagrams, what it did was just to remove this fictitious exponential decay, and we got the diffusion coefficient, and we got, yeah. Okay. So to summarize, I'm actually surprised that I'm actually at the end of the lecture as I planned. Okay. Okay, to summarize, how do we get diffusion in quantum mechanics? It's not that easy. First of all, you cannot think just about the propagator. You cannot just think about, I do something on the propagator. You really have to look at probability distributions. Probability distributions have products of the propagator. This is the correct thing, because also when you look at, for example, at the fluctuations of the local density of state, also that has products of the propagators. So in order to do that, there are diagrams which appear, which connect the retarded and advanced propagator. And they have to be taken into account at penalty of losing unitarity of your theory. Okay. There are other diagrams that I'm neglecting. For example, this here, plus all the maximally crossed diagrams, they are called the Couperon diagrams. The Couperon diagrams are the first weak localization corrections that they're actually able to capture what happens when you turn on disorder on top of just having a diffusion coefficient. They will give you a peak of the return probability. Okay? I'm not going to do that. That's too much. What I'm going to do instead is the following thing. So what we want to do typically, okay, so anyway, if somebody can actually do this, instead of going to the real space representation, discuss directly this thing P0 in Q omega by doing the convolution and manages to get this thing, please let me know, because at a certain point I had to stop calculation, but I would like to do that calculation. Okay, good. Let me connect to modern things, right? Modern things. Okay, good. Participation ratios. Okay, so participation ratios. So we know that, so this is the Hamiltonian. We know that this thing is equal to 1. Okay, But how many terms contribute to this sum? Yeah.
Can you write you say that is greater than 1 or something like that, or small d when you wrote the dimension, talking about the dimension?
Yes.
So it never enters, right?
It wasn't the Fourier transform.
Only except in the so
Oh, yeah. So you mean, sorry,
no.
to get this?
Yeah.
Yeah, okay, no, this is exactly the same kernel in any dimension. Any dimension. So you get the corresponding Gaussian in any dimension. This is a vector. Yes, exactly, which is very important. In 1D and 2D, there is already something that, first of all, with this calculation, you don't see anything wrong in 1D and 2D. Okay, spoiler, 1D and 2D, they are localized for arbitrarily small disorder. I'll show you why and how to get it in the third lecture. However, if you look at the Couperon diagrams, they give you something. The idea is the following: is that I told you that what's important is that this scattering within the localization within the Broglie wavelength increases the probability of returning. But in 1 and 2 dimensions, the probability of returning is already infinite if you make a random walk. Okay, so the probability that you stay within a mean-free path is very high. Okay, and if your wavelength is of order of the mean-free path, then you keep building interference, positive interference, and in the end you never delocalize. But it's not easy to see. It's not. I mean, it's not. In fact, it took some time for people to realize that 2 dimensions for arbitrary small disorder is always localized. Okay, good. So this is one. So how many terms contribute to this sum? Well, you can get this by computing this sum instead. Okay. So, for example, the second inverse participation ratio is the sum of the 4th power of the wave function. Okay, and if we have a nice plane wave, like in this case, then this is of order 1 over v, and you should get this of order 1 over v. Okay, because you get 1 over v squared when you square it, but then you sum over all x, so you get an extra power of v. Okay, can we get this from this calculation? The diffusion should know something about this, right? Yeah, so what do? We can, okay? Again, you need to take the product of R and GE. You need to take the product in a smart way. Let's see. And then I'll stop. So take GR of XXE, GA of XX, and let's add a small, actually, let me do this. Let me minus omega alpha plus omega alpha, E plus omega alpha. But then I'm going to take imaginary omega. Okay. If I do this, let me see. And I take omega alpha equals I eta. Then I'm going to send eta to 0. If I do this, then I have, let me use the spectral representation for this thing. I get psi A squared of x, psi B squared of x, sum over A and B, and then the denominator. E minus EA plus I eta, E minus EB minus I eta. So let me separate this sum into 2 terms. One which is diagonal, and so I have psi AX to the 4th, okay, divided by E minus EA squared plus eta squared. and off diagonal terms. Now, if I send eta to 0, this term here will be order 1. It's not divergent. This term here will diverge. And if you remember, if I do 1 over eta, then eta sum over A, blah, 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 E minus EA. Sorry, let me put eta inside. E minus EA square plus eta square, okay? Then this thing here is a Lorentzian. When eta goes to 0, it's a delta function, okay? So this, the entire sum is 1 over eta sum over A. Actually, let me go to the continuum. Integrand dA, rho of EA, density of states at EA, delta of E minus EA, times psi A to the 4th plus order 1. So the recipe is the following. Take the product GRGA, compute it at frequencies which are small and imaginary. When I send this imaginary part to 0, I get a divergence. The coefficient of the divergence is the participation ratio, multiplied by the density of local density of state editing. Okay. Now, let me use our diffusion approximation for GRGA. Okay, GRGA then becomes GRGA average GR XX E minus omega alpha GA XX E plus omega alpha becomes 2 pi density of state, local density of state XE. Sorry, this is not the local density of state. This is the full density of state because I just went from the sum to the integral. So this is the full density of states, not the local density of state. It's important. I did not forget to put in X here. There really is.
Starting from GRGA, and everything was in a point. So,
Yeah, this is as a function of X.
so rho A.
No. This is sum over A that becomes this. Okay. And this is a delta function divided by E and so forth. There is a pi here, of course, because this is the delta function, 1 over pi, this thing here. Okay, very good. So this and this is 2 pi local density of state times the diffusion XX of at frequency omega. So if I sum over X here, I sum over X here, this X dependence is fictitious. This is the Q component when Q goes to 0, 2 pi rho of XE. Okay. And this is the Q component when Q goes to 0. So it's 1 divided by minus I omega plus dQ square when Q goes to 0. Okay. And and so we have that, equating the two things, we have that pi over eta times density of state at energy E times the second participation ratio at energy E is equal to pi over eta, because this 2 pi divided by I omega is pi over eta. Pi over eta times the local density of state at E. Okay? So the participation ratio is in this approximation, is the ratio between the local density of state and the global density of state, which is 1/V. Okay? So we can compute participation ratios if we know the product of propagator. And we get,
This approximation is trivial. The result in this approximation is really trivial.
yes,
Seeing the non-trivial.
yes, yes. In fact, to see the non-triviality, you need to go to Effettov's book.
Or
And-
give up and give seeing
Hmm?
or you give up and give in seeing the non-trivial.
Yes, yeah. Also because it's essentially, okay, so let's put it this way. The supersymmetric method to treat the Anderson model is great, and it works in two limits. Completely random matrix, epsilon expansion around 2 dimensions. If you want to compute things in epsilon expansion around 2 dimensions, fine. If you want to compute things about random matrix, fine, perfect. Okay, you can re-derive all the results of Dyson, you know, all these things and more, okay? You can do this for more complicated random matrix ensembles. If you want to get the participation ratios for 3-dimensional Anderson model at the critical point, no way. Nobody knows how to do that.
Because the W is way bigger, it's not possible.
Yes. Because the way because the 2 plus epsilon expansion, this I will try to convince you in the third lecture, when epsilon equal 1 is really bad. I mean, it's not like a Wilson-Fisher fixed point, for example, you know, 4 minus epsilon. Then you put epsilon equal 1, fine. You find critical response which makes sense for the Ising model in 3 dimensions, okay? You find exponents which make no sense for the Anderson model. So that's why in the last years we have actually tried to revive all the ideas of actually doing a 1/D expansion around D equal infinity. Okay, because it might work better. Okay, anyway, so by the way, if you really take this thing and you compute the participation, take against it, compute the participation ratios, you don't find 1/V, you find 3/V. Okay, and the 3 comes from the Gaussian. And Lev was saying that, you know, 3 is fine, 2 is fine, 1 is not. Okay. So the diffusion approximation is not capturing ETH properly for these things. Okay, it's giving you the correct scaling, not the correct exponent. At one point where I can put the finger and say maybe this is why, because here we neglected this essentially by taking eta smaller than the smallest gap, right? So we can really isolate single state. While in computing this thing, we've done the opposite thing. We have taken the thermodynamic limit first, then we put omega, kept up omega finite, and then we're sending omega to 0. It's not clear that these 2 limits commute. And as a matter of fact, they don't. Okay. So this will be the point where I will put the finger on. But in other calculations, in random matrix calculation, this trick works actually. This trick is isolating the 1/eta divergence of those things here actually works in Effettov's book. So maybe finite dimension is not that trivial.
We never gave the multi-factor.
No, yeah, not with the difference.
From the locator expansion, because that's just locality.
Yeah, not even from the locator expansion. Yeah.
Only the supersymmetric method will allow.
Only supersymmetric method with the epsilon expansion.
With that, maybe less than 3.
Only D much less than 3. Very close to 2. People, I mean, there are some studies on Anderson localization on fractals with dimension between 2 and 3. And they don't agree with the calculations of Ikami to 5 loops in the epsilon expansion. I mean, you have to do some, you have 5 terms, you have to do some Borel summation, and then, you know, at that point you can get whatever you want. You can get, you know, the wiggle of, the tail of the elephant wiggle. Okay, I'll stop here.
Okay, so let's resume at 4:30 more or less.
Allora aspetta, questo sia proprio il motivo